So we're going to finish off Chapter 8 today. You guys will have a quiz on this tomorrow. That's Thursday. We'll also go through the Chapter 7 quiz tomorrow. You'll get your review assignment so that you can start working on that because your Chapter 7-8 exam is on Tuesday. Okay, and then after that, we just have one unit left, Chapters 9, 10, and 11. And then hopefully we'll have some time, we should have some time for review leading up to your diploma exam, which is Friday, June 16th at 9 a.m. Right? So we're going to see how we can use the exponential general equation that you're given on the formula sheet to solve different types of problems. One of those is for compound interest questions. So it's different than simple interest because with simple interest, the interest is only calculated once at the very end of the term. But with compound interest, the interest is calculated at regular intervals. The interest is calculated, it's added to the principal, and then the next time the interest is calculated, you have a higher principal because the interest from the previous time is added. And so the principal keeps growing, and because of that, the amount of interest you earn keeps growing. So it's a great thing if you are saving money, investing money, but not so great if you borrow money because the amount of interest that you pay would be higher than if it was just simple interest. And in most cases, banks use compound interest. So, like I said, it's a great thing if you are saving, but it hurts a little bit more if you are borrowing. So the effects of compounding depends on the frequency with which interest is compounded and the periodic interest rate which is applied. So to define accurately the amount to be paid under a legal contract with interest, the frequency of the compounding, it could be compounded yearly, which means once a year. It could be half yearly or semi-annually, so every 6 months. It could be quarterly, which is 4 times a year or every 3 months. It could be monthly, 12 times a year. It could be daily, 365 times a year. And the graph shows how the compounding frequency changes the amount of the investment. Okay, so the very top one is continuously, which would be daily, as opposed to monthly, quarterly, or yearly. So you can see that the continuous compounding or daily gives us the highest amount. That graph is higher. Right? So this just is used as a comparison. The more frequently the interest is calculated, the faster it grows. So again, we've talked about the different compounding periods. Annually is once a year, semi-annually is twice a year, which would be every 6 months. Quarterly would be 4 times a year, which is every 3 months. So we can write those values in there just as a reminder. This is every 6 months. Quarterly 4 times a year would be every 3 months. 12 times a year, monthly, so that is every month. Weekly is 52 times a year, daily 365 times a year. So there is a compound interest formula, and so it's given there, and all of the variables are defined, but you're not given this one on the formula sheet. We're going to do all these in terms of our exponential function that's on the formula sheet. Y equals A times B to the power T over T. So remember, Y is the final amount. A is the initial amount. B, remember, is our growth factor. So this is no different than what we used before for all of these parameters. T is the time, and P is our growth period. And like before, the time and the growth period have to be in the same unit. They'll either both be in years or they'll both be in months, etc. So as we go through this, we're going to use that formula because that's the one that we're given on the formula sheet. So let's see how this works to solve questions involving compound interest. The first example says that $5,000 is invested in a 7-year GIC. A GIC is known as a government or guaranteed investment certificate. So basically it's a contract. You agree that you're going to put so much money in and you're going to leave it in there for a year or 2 years or 3 years, whatever it is, and the government guarantees that you'll get this interest. So in this case, it's compounded quarterly at a rate of 3.5% per annum. Now, per annum means per year. And so you'll notice that because it's compounded quarterly, which is 4 times a year, and the annual rate is 3.5% per year, we're going to have to do some math to figure out what the quarterly interest rate is, because that 3.5% is per year. But it's compounded quarterly, so we're going to have to calculate the quarterly interest rate. We want to find the value of the investment at the end of the term and then also how much interest was earned. So using that formula, y equals a times b to the power t over p. We want to find y, the amount at the end. The initial amount will be 5,000. That's what we're starting with. Now we have to calculate b, the growth rate. So this is where we need to calculate the quarterly interest rate. So let's do it on the side here. Whatever we calculate the quarterly interest rate as, which we will do, we're going to have to add 1 to it. And the reason we're adding 1 to it is this. When you calculate how much interest this investment earns, you're always going to have 100% of what you had plus the quarterly interest added on to that. Your money is growing. You're going to have the entire 5,000 to start with plus the interest that you're going to earn after that first quarter. So that 1 represents 100% of your investment, the $5,000. Plus, then you're going to have the quarterly interest rate. Now, the annual interest rate is 3.5%. And remember, whenever you're working with percents, you change them to a decimal first before you do any calculation. So that's 0.035, but that needs to be divided by 4 to calculate the quarterly interest rate. Quarterly means 4 times a year. So you have to divide that by 4 to get what the quarterly interest rate is. So we can use our calculator to do this. 0.035 divided by 4. That is the quarterly interest rate as a decimal. And again, you have to add 1 to it because every quarter you're going to have 100% of what you had plus 0.00875 more. So B would be 1.00875. All right, so there's our B value. So we can put this into the equation, 1.00875. Now in this case here, it's a 7-year GIC, but it's compounded quarterly. Remember, T and P have to be in the same units. So there's a couple ways, different ways you can think about this. If it's compounded quarterly, which is 4 times a year for 7 years, that means you're going to have a total of 28 times the interest is calculated. T divided by P has to equal 28. It's compounded quarterly, which is 4 times a year for 7 years. 4 times 7 is 28. So your interest is going to be calculated 28 times. T divided by P has to be 28. So the way that we would get that is remembering that It's compounded quarterly, which is 4 times a year or every 3 months. So the growth period is every 3 months, and the time would have to be the total number of months that we have here. Again, it's compounded for 7 years, which there's 12 months in a year, times 7 years. If you go 12 times 7, I think that's 84. And if you go 84 divided by 3, you get your 28, which we said we needed. So that 28 comes from the fact that the time will be 84 months, because it's going to be compounded month or for 7 years, 12 months a year times 7 years. The term of that loan is 84, not loan, the term of that investment is 84 months, and the interest is calculated every 3 months, 4 times a year. This gives us our 28 that we knew that we needed to get. So, by working this out, we will get the value of the investment after 7 years. And we can put this in our calculator all in one step. Your calculator will do order of operations. We have the $5,000 initial investment times 1.00875 to the power 28. So there's the value of the investment after the 7 years, $6,381, and we would round to the nearest cent, so 30 cents. $6,381.30. That's the amount of the investment. That's why, which is the first thing we're asked to determine. The second thing we're asked to determine is how much interest was earned. So the interest will be found by taking the amount we have at the end and subtracting the initial investment of $5,000. The difference there will be $1381.30. That is the amount of interest that was earned from that investment. Okay? Looking at example 2. Kelly invested $2,500 for 4 years. It's compounded semi-annually, which is twice a year, and received $843.26 in interest. What was the annual interest rate? So if again we use that same formula, y equals a times b to the power t over p. Remember, y is the final amount, which in this case would be the original 2,500 plus the interest of 843.26. If you add those together, you'll get 3343.26. So that's y, the final amount. A is the initial amount, which is our 2,500. B is our growth rate, which is what we need to calculate. And remember, B will be 1 plus I, where I represents the semi-annual interest rate. So when we figure out what I is, that will be the semi-annual interest rate. We'll have to double it because we want to know what the annual interest rate is. So in this case here, it's going to be compounded semi-annually for 4 years, twice a year for 4 years. So whatever T and P are, when we divide them, we're going to have to get 8 because it's compounded twice a year for 4 years. It's going to be calculated 8 different times. So whatever we get for T and P, when we divide them, we will have to get 8. And so where does that come from? Well, in this case here, it's compounded semi-annually, which is every 6 months. It's compounded semi-annually for 6 months. The number of months that the loan, or I should say the investment, goes for is monthly, which is 12 times a year for 4 years. So T would be 48. It would be 4 years times 12 months in a year. T would be 48. And if you go 48 divided by 6, you're going to get your 8, which represents how many times the interest is calculated. Now, you don't have to do what I just did. I mean, in this case here, you could just say, well, I know the exponent on the 1 plus I will be 8, because it's compounded twice a year for 4 years. So it's going to be calculated 8 times. That is the exponent on B. That is the value of T over P. But there are going to be some cases where we have to find T or P, and so we need to know how those two go together to get the exponent. So that's why I'm taking the time to talk about that now. If we plug in everything we know into our equation, our y value is 33, 43, 26, and that equals A, the initial amount, which is 2,500, times B, our base, which is 1 plus I, and you remember I will be the semi-annual interest rate, to the power T over P, 48 over 6, which gives us our 8. So we need to solve for 1 plus I. And we would do that by first dividing both sides by the 2,500. So they will cancel on the left, and on the right, I should say. And on the left, we will divide 33, 43.26 by 2,500. So that gives us 1.337304. And that's what 1 plus I to the power 8 equals. 48 divided by 6 gives us the 8. Now again, we need to figure out what I is. I would represent the semi-annual interest rate. I can get rid of the power 8 on the right by raising both sides to the 8th root. That'll cancel with the power 8 on the right, but I need to do the same thing to the left side as well. I need to take the 8th root of both sides. So on the right side, you'll just be left with your 1 plus I, and on the left side, we'll use our calculator to take that 8th root. So on these calculators, you go 8 first, and then you go math, and number 5 in this list is our x root. We've already put the 8 in there for the 8th root. When I choose number 5, it changes that 8 to the 8th root of the previous answer. That's 1 plus I. It equals 1.037. And so to get I, we will subtract the 1 from both sides. You'll get 0.037. And remember, that represents the semi-annual interest rate. Our semi-annual rate would be 3.7%. So therefore, the annual rate would be 7.4%. You would double the semi-annual rate to get the annual rate. So there's that one done. So this next one, George invests $3,000 into an account that pays 5.3% per annum, which means per year, but in this case it's compounded monthly. How long would it take to the necessary month for his investment to double in value? So this is one where we need to figure out what T is. How long will it take for the investment to double? Again, we'll start with our equation, y equals A times B to the T over P. Remember, y is the final amount. Well, if we want our investment to double, and we're starting with $3,000, the amount at the end has to be double that, which will be $6,000. Amount at the beginning is 3,000, the amount at the end would be 6,000. B, our growth rate will be 1 plus, again, that 1 represents 100% of the investment, plus, in this case, the interest is calculated or compounded every month. The annual rate is 5.3%, which will be 0.053, but that needs to be divided by 12 to get the monthly rate. And again, B, our growth rate is 1 plus that decimal. The 1 represents 100% of the investment plus whatever 0.053 divided by 12 gives us for our monthly interest rate. So that's where we'll start with a calculation. We'll get the monthly interest rate, which is that decimal, plus 1. Your money is growing, so you have 100% of what you had plus 0.00441666, repeating more every month. So it'll be 1.0044. So I'll write it down in a rounded value, but we'll keep that number in our calculator. Now, again, T is what we are trying to find out. How long will this investment need to grow so that it doubles? P, our growth period, will be how many times a year it is calculated, which in this case is 12. It's calculated 12 times a year. And that's consistent with what we did above here. Okay, our p-value was calculated, I'm sorry, it's not 12, it's 1. I apologize, because it's calculated every month. Right up here, it was calculated or compounded semi-annually, so it was calculated every 6 months. The one above, it was compounded quarterly, which was every 3 months. In this case here, it's compounded every 1 month. And so when we calculate T, it'll be the number of months, which will probably divide by 12 to turn it into the number of years. But remember, T and P have to be in the same unit. So P is every 1 month. So T, when we calculate it, will be the number of months. So if you plug everything into the formula, Y is 6,000, A is 3,000, our growth rate is at decimal 1.0044, and there's more numbers there, and that's in our calculator, to the power T over 1, which obviously is just T. So when we calculate T, it'll be the number of months. But first you would divide both sides by the 3,000. And that'll give us with 2 on the left equaling 1.0044 to the power T. And now to solve this, we will convert. We will convert from exponential to logarithmic by starting with the base and cycling through. Remember, in either form, the bases are the same, so it'll be the log of 1.0044 log base 1.044 of 2 equals T. So we go to our calculator, and I'm going to use that decimal, the entire decimal. The base is our previous answer, that entire decimal, and we're taking the log of 2 with that base. So this would be how many months. Now, if you round this, normally you would round it down, but the problem with that is if you round it down, the amount will not be $6,000. It'll be less than 6,000. So this number has to be rounded up, which means you'll have more than 6,000, but at least you'll have double what you started with. So T would be 158 months. And if we divide 158 by 12, that's how many years it would be. Now it does say to the nearest month, so I guess that's what we'll write it as, 158 months. which is our answer because it's compounded monthly, so at the end of every month. So these examples all dealt with money. We've seen other examples where we're talking about growth and decay of, let's say, cells, or growth or decay of an object due to the half-life. So we've seen questions like that before. We're using the same formula. So again, those parameters are defined above, where y is the final amount, a is the initial amount, b is our growth rate or decay factor, I should say, t is the total time, and p is the growth period or the period time. We saw before that the base is 2 when it's doubling, 3 when it's tripling. The base is a half when it's half-life. Like we've seen on the previous examples, B would be 1.04 for an annual increase of 4%. You got 100% plus 4% more. If you have a decrease of 8%, that means B is 0.92. You're losing 8%, which means you're maintaining 92%. And you change that to a decimal. So just for some more practice for determining B and P for each of these scenarios, if a certain strain of bacteria doubles every 4 minutes, that means B, the base, will be 2. That's your growth factor. And our P will be the growth period, which is every 4 minutes. If the half-life of a radioactive substance is 6 years, B is a half, and our growth period is every 6 years. If an investment triples every 10 years, B, our base, would be 10, and our growth period would be every 10 years that is happening. If the population of a town is decreasing by 4%, that means it's maintaining 96% of its population, which means that B, our growth rate, would be 0.96. And this happens every 1 year. So that's our growth period. If the value of an antique is increasing 15% per year, B would be 1.15. 100% plus 15% more, and you got to change that percent to a decimal. And this again is happening every year, so that is our growth period, every 1 year. So, first example, in this case, you're given the equation. Sometimes you will be, sometimes you might not be, so you have to write your equation. The number of fish in a lake is decreasing at a rate of 7%, which means it's maintaining 93% of its population. That's why B, the growth rate, is 0.93. This is happening due to overfishing. We'll use this equation to see how many fish there will be in 5 years. So it'll be 2,500 times 0.93 to the power 5, which you can do in your calculator in one step. So the population should be less than what it was at the beginning because it's decreasing, and it is approximately 1,739 fish. Approximately. How many years will it take for there to be half of the original population? Well, if we start with 2,500, half of that will be 1,250. So the growth rate is 0.93 every year. We need to know what n is, the number of years it'll take to get there. If you divide both sides by the 2,500, you will get 1/2 on the left. Equals 0.93 to the power n. And we will solve for n by converting from exponential to logarithmic. Start with the base and cycle through. The base of the exponential function is 0.93. That'll be the base of the log. It's log with a base of 0.93 of 1/2. That's what n equals, and we can do that on our calculator. Remember, if you don't have the newer operating system and you need to use a change of base identity, it'll be the log of 1/2, which is 0.5 in brackets, divided by the log of 0.93. So how many years to the nearest tenth? 9.6 years. Okay. Number 2, in 2002, the population of a city was 160,000. It was increasing at a rate of 4.5% per year, annual. So in this case, we need to write our equation. So we'll have y equals a times b to the power t over p. A, our initial amount, is 160,000. B, our growth rate, because it's increasing at a rate of 4.5% per year, you're going to have 100% plus 4.5% more, which would be 0.045. And that will be to the power t over p, which will be 1, because it's increasing at that rate every 1 year. So essentially the exponent is just t, where t would be the time in years. So to determine the population in the year 2005, that means that it will have grown for 3 years. From 2002 to 2005, that population would have increased for 3 years. So we can calculate that in the calculator. $182,568.6. It doesn't say what to round it to, so we could round to the nearest person, 182,587. If the population continues to grow at this rate, how long would it take for the population to double? Which means that the amount at the end would be 320,000. And when you divided both sides by the 160, you would get 2 on the left. So this is the equation that we need to solve t for. Now again, you could let the left side be 320,000. That's double the original population of 160,000. But then your next step would be to divide both sides by 160,000. So on the left, when you divide the 320,000 by 160,000, you get your 2. We need to solve for t. We would convert from exponential to logarithmic by starting with the base and cycling through. The base of the exponential is 1.045. That's the base of the log. So we need to solve for this by using our calculator. Either use the change of base identity, or if you have the newer operating system, you can just type it in directly. Log base 1.045 of 2. I think it says to the nearest tenth of a year, so it'll be 15.7 years. All right. Number 3, a certain strain of bacteria doubles every 6 hours. So that tells us our growth factor is 2. It's doubling. When we use our formula y equals a times b to the power t over p, b, our growth rate or growth factor, will be 2. We want to know how many bacteria there were after 28 hours. So we want to know what y is. What is our final amount? Again, a, our initial amount, would be 350. As we said, our growth rate, our growth factor, will be 2. So that is b. T, We want to know how many bacteria present after 28 hours. So that is our T value. And P, our growth period, is every 6 hours. That's our P value. So we'll plug everything into the equation. T over P, 28 over 6, will give us how many times the bacteria doubles. And that's going to be a rational number, and that's fine, because it's continually happening. It's continually growing so that every 6 hours the amount doubles. But we can put this into our calculator all in one step. And there's a number of bacteria after 28 hours. If we round it to the nearest bacteria, 88, 89 bacteria. Number 4, patient who was feeling ill had a sample of bacteria taken from her throat. It contained 354 cells. So that is our initial amount. 24 hours later, the sample was recounted and contained 8186. So that is the amount at the end. We want to determine the doubling period. So that tells us that our growth factor is 2. The number of cells is doubling. We want to find out how long it takes for that to happen to the nearest tenth of an hour. We want to find out what the growth period is. And the time that has elapsed here is 24 hours, because 24 hours later, the sample was recounted. So that is how long the bacteria has been growing. So when we plug these all into our formula, y equals a times b to the power t over p. The amount at the end is 8186. The amount at the beginning was 354. Our growth factor is 2. T is 24. We want to solve for P. We would start by dividing both sides by the 354. Which gives us 23.124 approximately, equaling 2 to the power 24 over P. To solve for P, my next step would be to convert from exponential to logarithmic. Start with the base and cycle through. The base of the exponential function is 2, so that'll be the base of the log. It'll be log base 2 of that decimal, 23.124, which we have in our calculator, and that must equal 24 over P. We need to solve for P. So if you multiply both sides by P, you'll have P times the log equaling 24. So then you would divide both sides by the log to get 24, to get P by itself. So that's what we need to do in our calculator to get P by itself. 24 divided by log base 2 of that entire decimal, my previous answer. So we're asked to round this one to the nearest tenth of an hour. The doubling period is every 5.3 hours approximately. The number of bacteria is doubling every 5.3 hours. Number 5, a radioactive isotope has a half-life. So that means our growth factor is a half. That's what's happening to this sample of this radioactive isotope. Its amount is being cut in half. And we're told that the half-life is every 30 minutes. So that is our growth period, every 30 minutes. How long would it take? So we want to know what t the time is. For an initial amount of 320 milligrams to decay to a final amount of 10 milligrams. So those are all the values that will go into our formula. The amount at the end is 320. That equals the amount at the beginning, A. Our growth factor is a half. I don't know, is it? 10 is the amount at the end. It's starting with 320, that's our initial amount. It's decaying to 10, that's the amount at the end. Oh, I wrote them in backwards, didn't I? Thank you. I wrote them in backwards. T is what we're looking for over P, which is every 30 minutes. So T will be in minutes because remember, T and P are always in the same unit. So we need to solve for T. We would start by dividing both sides by the 320. So on the right side, the 320s will cancel. On the left, I have 10 divided by 320. So it's that decimal point 0.03125. That will equal 1/2 to the power t over 30. So I would solve for t by changing the form from exponential to logarithmic. Start with the base and cycle through. The base of the exponential function is a half, so that'll become the base of the log. I'll write it as 0.5. After the 0.5 comes the 0.03125. And that will equal t over 30. And we can get t by itself by multiplying both sides by the 30. So I got that decimal in my calculator. I'll go 30 times the log with a base of 0.5, the log of the previous decimal, the previous answer. We get exactly 150 minutes. So that tells me we probably could have done this just by using some logic. It's being cut in half every 30 minutes. So after 30 minutes, so if we go t our time and mg for the number of milligrams left. At time 0, we have 320 milligrams. After 30 minutes, the 320 will be cut in half to 160. After another 30 minutes, will be cut in half down to 80 milligrams. After another 30 minutes, after 90 minutes, will be cut in half down to 40. Another 30 minutes, which is 120 now, we're down to 20. Another 30, which is 150, we're down to our 10 milligrams. Okay. So we definitely could check our answer that way. Normally it's not going to work out that way. Most of our answers we've got have been decimals that we've had to round, but this one wasn't. Population of germs on a dirty countertop table doubles every 25 minutes. So that tells us that B, our growth factor, is 2 because it's doubling. It also tells us that our growth period is every 25 minutes. How long? T is what we're looking for, the number of minutes, because remember, T and P are always the same unit. How long would it take for the population to triple? So in this case here, we don't know what our initial number is, but we can just make up a number. If let's say that we started, if A, our initial amount was 1, then Y, the amount at the end, would be 3. If we use the formula, the amount at the end is 3, the amount at the beginning is 1. It's doubling, so our growth factor is 2 to the power T, which is what we're trying to find, over P, which is every 25 minutes. If you divide both sides by 1, you're going to get 3 on the left. And we would solve for T by converting from exponential to logarithmic. Start with the base and cycle through. The exponential function has a base of 2, so our log will have a base of 2. It's log base 2 of 3 equals T over 25. Multiply both sides by 25 to get T by itself. So it's 25 times log base 2 of 3. So the question says how long to the nearest minute? It would be 40 minutes when we round to the nearest minute. All right. This last example. In April of 1986, there was a nuclear accident at Chernobyl. It contaminated the atmosphere with quantities of radioactive iodine-131. So what happened is that the reactor melted down. It released all this radioactive stuff into the air. And to this day, it's still a dead zone. Okay? People that lived close to there died. Some of the people that survived, they had effects that they're still suffering from. Children that were born as a result of that, because their parents were contaminated, they were born with deformities because of it. Animals died. Animals were born with deformities. And there's actually some tour companies that organize trips that people can go to the site and see what it looks like now. And as of now, the amount of radioactive substances in the air isn't too bad, so most people, can go there with just very minimal protection, like face masks, things like that, right? But you could go there. So, in this case here, the half-life of the radioactive iodine is 8.1 days. So B, our growth factor, would be a half. And the half-life is every 8.1 days. So that is our growth period. This happens every 8.1 days. We want to determine the number of days, so we want to know what the time is. That's what we're trying to find out in days, because our half-life is in days, so that the amount at the end is 25% of the original amount. So if we said that A is the original amount, Y, the amount at the end, would have to be 0.25A, 25% of the original amount. Now, I'm going to use these two in my equation. We could do the same thing we did for the previous one. We could say, well, if we started with, let's say, 10 milligrams, then the amount at the end would be 25% of that. 0.25 times 10 is 2.5 milligrams. So you could do that. But at the end, you get the same value on the left, which will be 0.25. When I use the formula, y equals a times b to the power t over p, the amount at the end is 0.25a. If a is the amount at the beginning, our growth factor is a half, t is what we're trying to find, p, our growth period is 8.1 days. You're going to divide both sides by a here, which will eliminate them, and you'll be left with 0.25 on the left. As I said, if you let a be 10, and then y would be 0.25 of that, which would be 2.5, when you divide both sides by 10, you'll get the 0.25 on the left. So either way, it doesn't matter. But we want to solve for t, and we would do that by, again, changing it from exponential to logarithmic. Start with the base and cycle through. It'll be the log with the base of 1/2 or 0.5 of 0.25 equals t over 8.1. You can multiply both sides by 8.1 to get t by itself. And we can put this into our calculator all in one step. 8.1 times log with the base of 0.5 of 0.25. And t is approximately 16.2 days. Or to the nearest day, 16 days. And because the amount remaining is always 25% of the original amount every 8.1 days, there'll always be a trace of this radioactive substance there. When you take 0.25 of something, there's always something there. Okay, and there's a show on Netflix. I think it came out last year. There was almost a nuclear meltdown at 3 Mile Island. It was called. It was in the U.S. I think it was just outside of either Pittsburgh or Philadelphia. I think. Anyways, it's a show on Netflix. I think it's a 4-part series, and they go through what happened back then, and it almost melted down. There was some radioactive stuff that was released into the atmosphere, and some people did get sick, but it came darn close to being a major disaster, because that's the eastern seaboard is, the most populated part of the United States together. So it could have been catastrophic had it actually happened. Okay. There was also a movie, and it was a number of years ago, where a mother was accused of poisoning her baby. And the baby got really sick, and the doctors did tests on it, and they found this substance in the baby's system, and they thought that the mother was poisoning the baby by putting this chemical into the baby's formula. And then the lawyer got the mother off because of using half-life. The amount of substance that was in the baby's system, the half-life of that was, I don't know, every so many days. And the lawyer proved that if the mother would have poisoned that baby with that amount of material in its system, it would have had to have given the baby several gallons of this stuff, because of what the half-life was, and the time period that had gone from when the baby was first diagnosed till then, and what the half-life of this was. The mother would have had to give this baby gallons of this stuff, which wouldn't be possible. Baby wouldn't be able to ingest that amount. So the lawyer got the mother off, and with further testing, they actually found that the baby's own body was producing it. So just some weird genetic anomaly that was causing the baby's body to produce the stuff itself. But the lawyer got the mother off because of using what they know about half-life of whatever that substance was. Right? Okay, so there are, I think, 3 pages there that follow that have some questions involving exponential growth and decay as well as interest rates. You should do these for practice. I will post the solutions on Google Classroom. Tomorrow you guys will write your Chapter 8 quiz. We'll also go through the Chapter 7 quiz. I'll also be handing out the review assignment for you to start working on because you'll have your exam on Chapters 7 and 8 on Tuesday. Okay, so on Monday we'll go through the Chapter 8 quiz and you'll have the rest of the class to finish off that assignment, ask any questions that you might have. Once again, this review assignment is going to be really helpful for this test. If you can do everything on that review assignment without any problems, you'll be fine for the test on Tuesday. It tells you all the things that you really need to know. So make sure that you spend the time making sure it's completely done. It does count for marks. It's got to be handed in. But the other part of this is going to help you prepare for your test. Okay, so get working on the review or on these assignments.